economy at its best. Tourists using straws time over time, again until it's our last straw. A toy as a weapon of mass destruction. Could that be? This year, industry will produce 400 billion kilos of plastic, and 40% of that is thrown away in 20 minutes. That's throwaway living for real. For that, it's my conviction that we need a radical change, and the only way to turn the tide is when our health is at stake. 70 years of plastic captured in one image. Have a good look. Today, you will be witness of the first proof that plastic is a danger to humanity. But it's not too late. We can turn the tide if we want, and let's face it, with optimism and humor.
This little jar of cream, for example, it contains 1.5 million microplastics. Those particles are so small, if they enter your body, they can actually get into your organs.
I'm concerned about microplastics exposure for humans because of the risk of chronic inflammation.
I think it's reason for concern. Million microplastics.
If women in the Netherlands were to use this every day, we would be emitting a huge amount of microplastics to the environment just from using wrinkle cream.
I don't know if Olas is in the venue, but if you are, welcome. Let's clean up our act. I wish you a wonderful summit, and I'd like to introduce Cyril Guch, our partner in crime from Parley for the Oceans. Thank you.
Hey there, what's up? Plastic. So we're coming from a time where we were so excited that we could actually create things. We were so excited, and we had these ideas of mankind could improve nature. Nature had millions, billions of years to create the high tech that allows us to be here. There's like a super fragile ecosystem. But then last 50 years, we got like so excited by all these things that we can make, all these things that we can scale up, all these ways that we can like explore how business, how products can like be distributed around the world. And when you create something and you're so anxious that your creation, your invention could fail, that you often don't allow to really think it through. And I guess that's what happened with plastic. That's what happened with a lot of materials, a lot of ingredients, a lot of substances. Plastic is just this perfect flag, this perfect symbol of a toxic age that we created. It's a design failure because it doesn't fit in a circular economy, even if you recycle it, even if your end of life, end of use, take it back. It created already so much damage while it was made, while it was used. Because plastic is not that solid, safe material as it was communicated in the last decades. It got communicated to us as this wonder material that keeps us safe, that protects us. But in reality, it sheds, it leaches, it gases even off. So this plastic material is never like glass, or never like a substance that protects the content without infusing something into it. And as a designer, I would just say, we need to let it go. We need that material, it needs to go because we are not able to harness it. As we have to let go of a lot of other ingredients. A lot of materials that we're using every day, every moment in our life, and that are in this amount that we're pushing out, not anymore acceptable. So today is for us at Palais an important day because we have the feeling that Maria, with her work, and of course everybody who's involved, is opening or are opening a next door to the end of plastic, really. And it's a door that you couldn't have opened so much earlier because people simply didn't want to hear, and the lobbies were too strong. But now, in 2019, nearly end of the year, we know that plastic is the new tobacco in the eyes of the public. It's not anymore the safe material that it pretended to be. And the consumer doesn't want to be anymore the litter bug, the one that carries the responsibility for this material because they're putting it probably in the wrong bin. Because that was the strategy. That was the strategy for lots and lots of years, and that's also the whole intention behind the 3 R's, reduce, reuse, and recycle. Because these 3 R's say, oh, the material is fine. Don't make it waste. Don't let it go to waste. We're using it wrong. We can say the same about weapons. I believe we need a new strategy. And this strategy we call AIR. Avoid, intercept, and redesign. We can avoid plastic, but sometimes we can't yet because we depend on it, we're addicted to it. In these cases, we can at least use recycled material, intercepted material. But the true solution for all these problems that we are facing today is new materials. We need to redesign this material. And we shouldn't be anxious just because it looks like a big idea. We shouldn't be anxious because some people invented it in the first place. And it's not so complicated. It just needs money, time, and willingness. It's a design challenge, really. And today, with everything that we're going to learn today, we're going to bring it home. We're going to bring it under the skin of everybody. And I believe and I agree in what Marie said, that once people understand that it hits them personally, it's not only these animals, these poor turtles and whatever creature dies of that debris, but it's my family, it's my kid. And I'm actually suffering of the consequences, not making this decision, not like smoking the cigarette myself, but being the one sitting next by. So I believe that this is a legendary moment, and I'm very grateful to be a partner, and I'm very grateful to be here, and I thank the plastic movement that had started way before we were in place. And we joined 7 years ago, and we boosted as much as we could, but the true heroes are out there every day, and these are 10,000s of activists, 100,000s of activists now, growing into the millions. And I'm very grateful and thankful for that movement. Thank you.
Cyril, you just came in from New York this morning, and Maria, please come on the stage. What do you hope that the people here, the audience in the hall, will go home with today? What should they learn? What should they hear?
I think, first of all, it's probably a new idea for a lot of people that these solid objects, these pieces that we know from everyday life, that they're actually zombies that are luring up on you, and they actually can enter your blood, can enter your brain, and probably cause things that you would never ever believe. What I hope is that everything what we see, what we learn here, encourages other scientists to deliver more and more evidence, because I think the ears are wide open right now. Oh yeah.
So I'm a big...
A plastic tea bag?
Yeah, this is what I like to drink every morning, and I'm probably really informed about this whole problem. Is this a killer thing that
I think every tea bag right now, even the paper ones that look like paper here, it's very obvious. It's obviously synthetic fiber, and heat plus synthetic fiber is not a good idea. And we're going to learn hopefully more today, but you don't want to put heat on plastic and you don't want to consume it. But even the paper stuff, yeah, we should probably pick it up again and recycle it.
Okay, I will. Just wanted to share. Listen, thank you very much. I will speak to you later today. Maria, there is a lot of research money now flowing into this subject. We're going to talk about that. 15 projects have been started up since the beginning of this year in April. 7 scientists are going to present their preliminary results. We have to underline that. But it is quite a thing. I mean, to have all these people here, I know some of them are maybe a little nervous because it's the first time that they are talking about this in public, right?
Yes, it is, and it's thanks to Sonnenweg. Thank you, Sonnenweg. They financed those 15 projects, and the first results are quite spectacular, I would say, and the scientists would say, let's take it easy.
Well, we're going to listen. First one is to give an overall view of this problem is a professor at the Vrije Universiteit here in Amsterdam, Dick Fetal.
So, good morning, everybody. When people ask me, do I have plastics in my blood? I have to tell them I don't know. And the problem is that we're not able yet to measure the very small plastic particles. And these are the plastic particles you can expect to occur, to be present in your blood. Personally, I think they quite likely that you have these plastic particles in your blood. But I think it's just a question of time before we can prove it. What I do know with certainty is that everybody also here in this theater, has chemical additives, plastic additives in his blood. Probably at low concentrations. And these additives can leach out of plastics. We know that, we heard that already this morning. There you go, and this is my age, you know. And I forgot things to say, you know. Yes, of course, these additives can be toxic, we know that. There's quite a number of them that can be toxic. They can be carcinogenic, or they can even be endocrine disrupting chemicals that can cause effects at very low concentrations, for example, on the developing fetus or the newborns. There's mounting evidence for that. So there are two things here. We have the chemical additives and we have the plastics. And these are two different things. Plastics are made of monomers, petroleum based. And they're solid materials, they're non-degradable. And the additives are compounded in the plastic to give it certain properties, like flame retardants or phthalates. So the thing is, as humans, we are exposed, in fact, to both the chemical additives and the polymeric material, or fragments of the polymeric material. So, I think it was about 30 years ago, you can see from this picture here, that I was doing a lot of research on plastic additives in the North Sea. And at the time I had no idea about, of course I knew that plastic is non-degradable, but I had no idea about the accumulation of the plastics in the seas and the oceans, you know, the scale of it, the global scale. No idea at all. It even didn't cross my mind. You know, the fragmentation of this litter into amazing amounts of little micro and maybe nanoplastics. You know, it didn't cross my mind at all. I think these terms like plastic soup and microplastics, they were coined maybe a decade ago. And it is only just very recently that we recognize that we are dealing here with a human health issue as well. My colleague had a lesson, we published this paper, opinion paper in the Environmental Science and Technology, just expressing our concern about those microplastics. And we called therefore for research as well. So, what are microplastics? Basically, these are plastics in the environment that are smaller than 5 millimeters. Some of them you can just see, but most of you will not see them. You know, they can be as small as a bacterium, which is 1,000th of a millimeter. They can be even as small as a virus, which is let's say 100 nanometers. Now, for comparison, what is a nanometer? Well, you can, the nail of your finger grows 1 nanometer every second. So these are very small, tiny particles we're talking about here. These microplastics, they are quite diverse in terms of sizes, chemical composition, and shapes. And in fact, you know, if you look at the composition, you can see they consist of hundreds of maybe or even thousands of different polymers. And the additives, there are numbers, maybe also thousands of additives there that are around in the environment, and on the plastics as well. And the plastics have also the capacity, they absorb the contaminants from the environment, like PFAS, for example, or pesticides, or even metals. So we have, it's not one pollutant. Microplastic is not one pollutant, it's a cocktail. And almost every microparticle has its own identity. It is an own cocktail of very complex cocktail, highly complex cocktail of contaminants. It is really, you know, I'm a toxicologist, and it is really poses really a puzzle, you know, to work with these microplastics. Meanwhile, we understand readily that these microplastics are everywhere in the environment. You can find them absolutely almost everywhere in every environmental compartment. They are in the water, they are in the food, even in the air. And so we are very, we are exposed. I always say, you know, it's almost like you are surrounded by a cloud of microplastics, and it goes with you all the way you go. And to demonstrate that, if you take mussels, mussels are filter feeders, so they filter the water, ingest microplastics. We know they have relatively high concentrations of microplastics. If you put a plate of mussels on your kitchen table, and you leave it there for 2 hours, there are more microplastics on your plate and on the mussels than in the mussels themselves. So that means that everything is in fact contaminated with microplastics. Yes, what does that mean? Does it harm us? Well, there are basically 3 potential health risks, and we call that hazards. It's not a real risk yet, but it's a hazard. And there are the visible, what we call the particle toxicity. There are the chemical effects of these particles, and there are microbial effects of these chemicals, of these particles. Now start with the particle toxicity. Size is very important. It's in fact just crucial. The smaller the particle, the more easy it can actually penetrate your body or penetrate very deeply into your lung and can make a trip in your body. Key is that that we need to find out how much of these particles actually do penetrate your body, end up there, and accumulate somewhere. Because we know these particles, like chemicals, they go in your body and they go outside of your body. It's only a very small percentage that really are retained in your body. Once in your circulation, they can imbalance the immune system. They trigger a cascade of molecular cellular effects that causes oxidative stress, DNA damage, even inflammation. And that is paving the way to other diseases as well, particularly if it's getting chronic inflammation and systemic. So this is not a good thing for your body. There is no hard proof for this in humans yet. There's no hard evidence. But we have some evidence from occupational exposures where workers in nylon factories are exposed to nylon flocks and develop lung diseases, for example, some of them. Exposed to high concentrations of both. We have examples for example, from lab animal studies with rats and fish. If you feed rats with high concentrations of polystyrene powder, for example, or nanoparticles, you can see rapid take-up in the intestine, translocation into the circulation, and it is accumulating in certain organs, including the brain, and perhaps even maybe the placenta. So these indications are quite interesting and very strong. There are also similarities with particularly air pollution. And we know that is quite a big killer in the world. We know that the fine and ultrafine particles can, the WHO estimates about 6-7 million people worldwide die early from exposure to fine dust. Now, we know that the particles are in the air as well. Our estimation is that about 3 to 7% of these fine particles in the air consist of rubber tire particles. So that's some plastic components of 3 to 7%, and there's more there, of course, there's more than just rubber tire dust. So, as a toxicologist, you said, okay, well, so what? Because you first have to prove, what is the composition of these particles? How is it ultrafine material? And the second thing you have to solve is, how toxic are these particles compared to soot particles, for example, from diesel exhaust? But these are pressing questions, I think, that really require urgent research, because they can have quite a substantial impact on health and on the disease burden in general. Now, then we have the second one. These are the chemical effects of particles. And the chemical effects of particles, that it's likely that, that particles can hitchhike, and when they enter your body, you can bring chemicals into your body, and maybe contribute to the total load of chemicals in your body. That's likely, to a certain degree, probably it's likely. However, I think it's a greater hazard is perhaps that these particles can bring, for example, carcinogenic pH deep inside of your lungs and contribute to cancer. Or they can, once in the circulation, they can deliver neurotoxins or endogenous chemicals in organs like the brain or the placenta. So these potential chemical effects, they require in-depth research, as far as I'm concerned. I think that could be very crucial. And finally, we have a third type of hazard, which are the microbial effects. And microbial effect is something discovered a couple of years ago, that anything in the environment, any plastics in the environment, develops a little layer of life on the surface. It's a very unique little micro-ecosystem, in fact. And that layer, we call biofilm or corona, whatever, contains dangerous bacteria, for example, pathogens, human pathogens. Vibrio cholera has been identified there. The thing is that some of these pathogens, they thrive much better on plastics or certain plastics than on natural substrate in the water. So that means, first of all, the plastic can disperse the pathogens, and secondly, if you're in contact with them as a human, they can increase the infection rate, for example. Again, this is an example. I mention this because if you put that in context of an epidemic, for example, like in Mozambique now with cholera, or Indonesia, where after flooding or natural hazards you have often an outbreak of an infectious disease. If you put there, together the susceptible population, poor hygienic conditions, and at the same time high levels of plastic pollution, these factors come together. I think it's possible that plastic could play a role there as a factor, spreading these pathogens, increasing, contributing to these epidemics. So I think this is something that needs to be researched. I think we have to find out about it as soon as possible, if that's the case. It's a hypothesis, eh? Okay, well, let's try it. Let's test it. Then, so you can see, ladies and gentlemen, dear audience, you can see there are numbers of knowledge gaps, and as I mentioned here already. And I was a bit surprised myself, you know, a couple of weeks ago, 6 weeks, this report from WHO on drinking water microplastics, they came out and they claimed, you know, there is no harm, there's no risks of microplastics, you know. What is this? To be honest, you know. Because the thing is, it's based on the information available today. And what is this information? This is, we have is only the data of the larger microplastics. The stacking numbers of micro nanoplastics are not considered yet in this assessment. So for me, it has a low relevance in that case. But the good thing is the report also asked for urgent research at the same time. So very happy about that. And so we can see at one side there's quite potential for exposure, and there is quite potential for hazards. But there are huge knowledge gaps and uncertainties in doing a proper and adequate risk assessment. And so we need to know more about, for example, we need the technologies, the analytical methods, you know, to measure these very fine particles in blood, for example. And there's work done already on that. So maybe we hear about it later a little bit more. We need to know where these particles go in your body. How much is entering your system? Do they indeed go to even reach the placenta or maybe accumulate in your brain? And then we talk about the very small ones. And how is the immune system coping with it? How is the immune system coping with it? So these are very critical questions that should be answered before you can do a proper risk assessment. So I was particularly very happy that a couple of months ago, this Zon and Way program started on microplastic and health. It's 15 projects, and it's pioneering work, 1 year projects, but it is trying to answer some of these burning questions. And what is so special about it? Well, for me, it is very special because you work in multidisciplinary teams. You know? I am an environmental toxicologist. I work together with the medical specialists, the medical sector. I work together with food safety people. And this is a very strong combination. And the other thing is, it has been said already, we are in the Netherlands a front runner of this type of research. Anyhow, am I concerned? Yes. As a scientist, I am really concerned about this. I think it's important to find out how and at what concentrations these microplastics do pose a health problem. Globally, we know that the levels will increase. Even if we stop with plastic pollution right now, you know, there will still be increasing levels of microplastics for decades. So, is there a risk, a real risk? I don't know, but I think we should find out as soon as possible. And not maybe just for our health, but for the future of our children. I think there is no time to waste here. Thank you.
everybody. Wow, as far as science events go, this has been quite great so far, and there's no plastic in sight, which is amazing. So I've been working on this issue now for what feels like a while, and I know there are a few of us in the audience who have too. For me, it began back in 2011 when I was studying for a PhD focused on the impacts of microplastics on marine worms. During this time, there was evidence emerging to show microplastics in shellfish. So there I was, working on worms, looking at harm, all the while in the knowledge of our exposure to microplastics. And so that triggered my interest and concern. And so I joined the Medical Research Council Centre for Environment and Health to begin addressing some of the knowledge gaps across from human exposure to accumulation to toxicology. So there's been a wealth of work done by great researchers around the world focused on impacts and occurrence of microplastics. But today I'm going to follow up on some of Dick's presentation and really flag some of the knowledge gaps in relation to health and address where we need to be directing our research. So first, I think it's important to look at this as a holistic issue. So we've already heard how widespread this is. Now, back in 2015, Jenna Janbeck and colleagues published a seminal paper on mismanaged plastic waste. They estimated that in 2010, between 4.8 and 12.7 million tonnes of plastic waste entered the environment. Now, that's plastic as large pieces ready to degrade into microplastics. However, that represented just between 15 to 40% of the total mismanaged waste in those areas. In other words, the majority was still on land, where it's susceptible to the same degradation pathways that it undergoes at sea. So degradation by sunlight, and when we combine that with sources of microplastics from abrasion, such as abrasion of synthetic clothing and synthetic tyres from cars, we can see that this really is an issue here on land too. So we're exposed to a range of microscopic particles in our food and in the air on a daily basis. And as Dick's already mentioned, there are associated health effects with these exposures. So we know, for example, that air quality can affect cardiovascular and respiratory health and in fact cause disease. And they're some of the biggest risk factors of mortality worldwide. So when we consider microplastics, and that's especially in the air, we can consider them a new component or a newly recognised component of this particulate matter, because the reality is they've probably been around us for quite a while. That's because the same abrasion and degradation pathways are just as applicable to back when mass production started in the 50s as it is today. So really, this isn't a risk, it's probably something that's been around for a while. The real question is, what contribution do microplastics have to these particle loadings, and how do they affect the associated health outcomes that we already see? I'm sorry, I'm going to keep drinking water. I had a cold earlier, so I've got a very dry throat today. So we've touched on the complexity of microplastics, and really we should consider them a class of pollutants rather than a type. And it's this complexity that really makes it difficult to predict and explore the health impacts. So we've heard about the additives and the microbes and the absorbed compounds, and I want you to think of this from an age perspective. So if we consider two different microplastic particles formed from the same way or formed in the same way at the same time, separated at birth, if you like. If we sample one from a coastal sample, it's likely to be rough and degraded and have an etched surface. It harbours microorganisms. It's probably got foreign chemical compounds on its surface. And then, because we've sampled it from the coast, the likely pathway to us is via a plate of shellfish or a mussel or an oyster. So what does this matter? You know, does the microplastic contribute any chemicals to our body? Is the dose so small compared to the actual muscle tissue that it doesn't matter? Are new chemicals generated in the cooking process? And what about its sibling, its counterpart, the microplastic that's freshly generated when we open a plastic bottle? It looks fresh and clean on the outside, but it's likely got quite a high contaminant burden on its inside from all its additives. And so these are the things we need to consider when we start to think about health. And you can see when you've got microbes and contaminants and additives and shape and type of plastic and size, that it's really difficult to start teasing out these variables because each one has its own impact on our biology. Now, one place we can look, this is the complexity of plastic, as I've just mentioned, one place we can look for answers is in the workplace. This is a very slow animation, I'm sorry. One place we can look for answers is in the workplace. So there are industries where individuals are exposed to very high levels of plastic dust, typically via the air. And one of these perhaps best known examples is flock workers' lung. So this is people who work in the flocking industry, establish this lung disease. Now, flock refers to shortcut nylon fibres, and during the cutting process, typically when a rotary mill is used, a very fine respirable dust is generated. It's important to note here actually that the dust itself is not fibrous. It's more like particles and elongated particles rather than actual fibres. But upon exposure, patients typically present with respiratory issues, so they have shortness of breath, they have cough, they have chest pain, and then the tissue shows inflammation and in worst cases, scarring. Now, typically removing patients from the workplace is enough to reverse the effects, and it's an effective therapy, but in the very worst cases, irreversible damage manifests and the patients don't recover. Now, of course, this all happens at very, very high concentrations. We don't know how this translates to our environmental exposure. But what has been seen is that similar tissue responses have been observed for people exposed to polypropylene, polyethylene, and rayon fibres as well. And so the question is this a plastic issue? And other responses observed in the airway similarly was observed in other tissues. Now, animal studies have also replicated these observations, so when nylon flocking dust has been tested in animal models, mainly rats, via inhalation, inflammation has been shown in one study 24 hours post-exposure to a single very high dose. However, the inflammatory effects did go back to normal after 29 days. But interestingly, an industry study that essentially looked at the same type of dust didn't find any inflammatory effects. So we've got a big question mark here, and this is really emphasises the fact that we have a sporadic evidence base, sometimes with conflicting bits of conclusions. But what authors have noticed in other studies when animals have been exposed to polyurethane dusts and polypropylene dusts is that there's a tissue and inflammatory response quite similar to what's observed to other types of particulate matter. So again, here the question is this a plastic effect or is this a particle effect? And that's something we really start to need to figure out. Now, there has been a few recent publications looking at the effect of ingestion. There's a bit less on new studies on inhalation exposure routes. But recently, a study looked at the effects of polystyrene microbeads of different sizes on human gut cells and in mice. Now, they found toxicity at the very highest doses up to the smallest microplastics. But when they fed the mice the same microplastics, they found some accumulation in the small intestine and intestinal tissues, but they didn't actually find much dispersion away from there. And this high concentration leading to toxicity and the fact that there was limited effects observed in the mice led these researchers and the German Federal Institute of Risk Assessment to conclude that polystyrene microplastic ingestion is of low risk to intestinal health. Now, this is all probably prior to the knowledge of the very high doses of microplastics we get from a fancy cup of tea. And also, I want to ask, how representative is a polystyrene bead? You know, we're not exposed to polystyrene beads, we're exposed to fragments and shards and really irregular shapes. And so there's a real question mark here over the role of shape and how that influences cellular interactions and harm. Because we know, for example, that fibres can cause harm in our immune cells. So our immune cells are there to essentially try and clear up all the debris and foreign particles in our body, in our airways and gut. And what typically happens with fibres is that they struggle to remove the long ones, the ones that they can't fully enclose. And because they're secreting lots of chemicals to try and break down this foreign particle, they end up causing lots of tissue damage to themselves and surrounding cells. And so the question is, does this happen with plastic fibres too? We know it's the case for asbestos and carbon nanotubes, but what about plastic? So So at King's College, we're really focused on the air. We are aware that we need to consolidate concentration exposure values, especially in health-relevant fractions. So we've been applying Raman spectroscopy and spectral imaging to try and detect these small microplastics in air samples. We've also been applying these methods to tissue with a focus on lung tissue biopsies to find real-world evidence of plastic uptake in the lung. And then, of course, we want to link external exposures and internal uptake and pathologies with the knowledge of what mechanisms are driving those effects and essentially what parameters of microplastics cause toxicity. And we're doing this in human lung cells. Now, this is all very current research, so for those interested, please come and find me, because the results haven't undergone peer review. So moving forward, we're in a knowledge acquisition phase, it's exponential, and so I think we need to take some responsibility and generate some robust, transparent evidence, because we have livelihoods and economies, and the environment and health depending on these outcomes. But where do we take this moving forward? We need to fully characterise what we're exposed to, and that's concentration, size distribution, chemical profile, microbial profile. We need to understand exactly what we're dealing with when it comes to health effects. And of course, there's the idea of the chemical leaching. You know, do microplastics act as a carrier? We've got to understand whether they actually contribute a relative dose of their associated chemicals to us, and if that pathway is meaningful compared to other pathways of our exposure to those chemicals. And finally, we really need to start testing relevant microplastics, so the stuff that's actually in our food, in the air, in the environment, and really figure out how specific those effects are to plastic and not just to particles. I think that's a real question moving forward for us as researchers. So that felt very fast. It was very fast. But thank you very much for your attention, and thank you to the organisers for having me, and I can't wait to have a discussion and hear all your results.
Good morning. I'm Ingeborg Koten, and I work at TNO, and I work in a group where we develop new measurement techniques, and we do this because we want to investigate the impact environmental pollution has on human health. And I'm also a scuba diver. And as a scuba diver, I've seen amazing sea life. And I enjoy the impact that this has on me. And however, in the deep sea, it's not possible to observe the nano and microplastics that surrounds me. These are invisible for the human eye, even with goggles. And in addition, I don't have a clue what actually the health risk of these particles is to me. So talking about risk, the words hazard and risk are often confused with each other. And, but understanding the difference is very important, and I would like to take you with me in that journey. And to explain this to you, I would like to take you into the water with me. Not to look for microplastic, but in this case, for fish. If we encounter a single fish all by itself with a low hazardous nature, for example a piranha, the total risk being the equation of exposure times hazard is rather low. Well, if we now encounter a whole group of piranhas, so we have a rather high exposure, but we have that same fish, we still have the same components, the total risk now becomes intermediate. But if we now encounter a complete different species with a rather high hazard, now for example a shark, but the exposure is still limited because the cage we're in, then the total risk is still intermediate. And now in the fourth situation, we have a higher exposure because we're in open water and there are several sharks surrounding us. Now, this is really a situation of high risk, and actually you don't want to be therein unless you're fake funk. So, to answer the question whether human health is at risk in case of nano microplastics, we have to study, next to the effect of the particles, which is very important, we also have to quantify the exposure part. And the exposure part consists of two important things. First of all, via which routes are we exposed? What are we exposed to? And how much is it? And secondly, what do we take up in our body? Because if we inhale 1,000 of particles, but we exhale them as well without a biological interference, well, there might be a rather low risk in the end. So, if we want to now quantify that exposure part, we actually run in some troubles. Because first of all, there are presently no quick and easy detection methods which are able to measure particles below the 1 micrometer. And especially below that 1 micrometer, it turns out to be becoming biologically irrelevant. Secondly, there's no standardization in the methods which are being used presently in sampling and analysis of the plastic particles. So this means that it's very difficult actually to compare different studies which have been published. And sometimes it's even not possible at all. And maybe most importantly is that, it is not one compound we're looking at. It's not one fish. It's this complete, complex mixture of different particles with different shapes, different chemistry. So, and here, it was already mentioned before, there's a similarity with particulate matter, the air pollution that we breathe in. And actually, at a traffic site, just at a busy traffic site, we breathe in millions of particles with each breath we take. So the human exposure routes are threefold. We have the skin, application of cosmetics, for example. Secondly, the inhalation route, when we breathe in. And thirdly, the ingestion route, so if we take in food or water which is contaminated. Whether a particle is now removed from our body or taken up is influenced by the particle characteristics. And so mainly the size and the surface chemistry play an important role in that. And in general, we can say that as the particle size decreases, the intake is increased. And for this, nanoparticles are especially a major concern. Personal care products containing microplastics could be a source for exposure via the skin. However, our skin is has a very protective barrier against particles. And although accumulation of the nano-sized particles has been found around hair follicles, no deeper penetration in the layers below have really been observed in studies up to date. And these points mentioned, together with the fact that the cosmetic industry is planning to phase out the use of plastics, luckily by 2020, this makes the skin as an exposure route of less relevance compared to the others. Because the second inhalation route is the second exposure route is the inhalation route, and was mentioned already also before is that especially in the occupational setting, especially in the textile industry, millions of particles have been found per cubic meter. And we can probably also expect these kinds of numbers in, for example, the recycling industry. But also in our everyday life, textile fibers from clothes are an important source. And studies have shown that 60 fibers per cubic meter have been reported for indoor situations. For the outdoor situation, car tires seems to be an important source for plastic particles in the air. And our own measurements have shown that up to 1,000 particles per cubic meter are present in the air. However, we should also realize that this 1,000 particles, it's only 2% of the particulate matter mass that we breathe in at the busy traffic site. So it's a rather low percentages of all the other particles we already breathe in daily at a traffic site, for example. Well, we have to say that the lung is very well capable of removing particles. In our upper airways, we have very efficient clearing mechanisms, and in the lower airways, we have specialized cells which can take up particles and remove them. But especially the nano-sized particles might be transported over the air-blood barrier and end up in our blood. And there actually have been studies with other nanomaterials which have shown that 4% of the applied dose was taken up in the blood. Looking at the third exposure route, ingestion, that is considered to be the main route of entry of plastic particles. And microplastics have been found in water, only a few numbers in tap water, but up to 5,000 numbers per liter for water in reusable PET bottles. And for beer, around 30 fibers and fragments have been reported. And what was already mentioned, also seafood, for example, mussels, contain 800 particles per portion. As well, other food components like honey, sugar and salt contain particles, but to a lesser amount, around 1 particle per portion. Well, in general, it is expected that the cellular uptake in intestine is limited, but that the uptake is increased with a decreasing size. And studies performed with nanomaterials have shown that around 1% to 2% of applied dose is passing the intestine barrier. So when we were considered to be exposed, not only to a single compound of a known hazard, but to a complex mixture of micro and nanoplastics of different sizes and shapes, it's essential that we, in the first place, develop a new pair of goggles to actually see and detect and analyze the microplastics, especially those are smaller than 1 micrometer. And second, that we standardize the methods and experiments so that we can actually compare different studies. And only then we will ultimately be able to conclude whether microplastics cause a health risk or not. Thank you.
So good morning, everybody. My name is Francine van Dijk. I will tell you about the impacts of plastic microfibers on our lungs. So for this, I will take you with me to my house. Every morning when I wake up, one of the first things that comes to my mind is, what will I be wearing today? And for those of you who wonder, this is really my closet. So this morning, in a rush, I ultimately picked this outfit, This shirt, it's made of cotton. I'm sure that many of you recognize this early morning dilemma, and therefore I'm curious, what are you wearing today? And do you actually know what material it is made of? The reason I'm asking is because clothing textiles release micro and nanofibers to the environment during the production, use, and at end-of-life disposal. And because the majority of all textile items now are synthetic, for example, made of polyester or nylon, this means that these fibers are mostly plastic. So they form a significant portion of all plastic pollution. So this means that when you wake up in the morning and decide with a sleepy head what you will wear that day, that this can have consequences for your direct environment. Those fibers are abundant in the air that you breathe in. And you're probably not aware that in your family house, so the house where you live in, per year approximately 20 kilograms of dust accumulates. And of this 20 kilograms, 6 kilograms is microplastic fibers. And because you spend most of the time indoors, this means that the exposure is pretty high. But can we actually inhale these fibers? And if yes, do they have an effect on our lungs? The honest answer is that there is not much knowledge on this. But what do we know? We know from this one study conducted in the 1990s that plastic microfibers can be found in human lung tissue of several patients. So clearly these fibers are inhalable. But what happens next? Do they just stay there, or do they also have an effect on our lung cells? As touched upon before, there are reports from people working in the nylon flocking industry that suggest that these fibers can actually be harmful upon inhalation. Let me think again. But in order to determine, so this suggests, these reports, that these fibers actually can have an effect on our lung cells. But in order to determine what effect this could be, we need a little background on the architecture of the lungs. And I gave you already a little spoiler. Have you ever thought of the lungs looking like an upside down tree? So air flows in through the root of the tree, the trachea, to the branches, the airways, into the leaves, which are the alveoli. And in these alveoli, the gas exchange occurs, so oxygen can be taken up into the blood. And when we then look at the inhalation of particles, we know that particles around the size of a hair, so approximately 100 micrometer, they can enter the throat and cause irritation there. Smaller particles like dust or pollen can reach into the airways, where they can cause inflammation. And even smaller particles, like particles from diesel exhaust fumes, they can reach all the way into the alveoli. And you can see here that they look like a little bunch of grapes. And these particles can cause damage there. So let's have a closer look at the cell types that play an important role in keeping dangers out and helping with repair when needed. So imagine that our lungs are music venue Paradiso. On a busy Saturday night, people flow into and out of Paradiso like molecules and small gases do in our lungs. An important condition for this to keep functioning is a solid building with robust walls. The inner walls of Paradiso can be seen as epithelial cells. They protect the structure of the building and prevent serve as a barrier to people not invited to the party. Then next we have the technical crew. And these support where possible and prevent the building from breaking down during the party. These are the fibroblasts, so they provide internal support. And then lastly, we have the macrophages, and these are the security. So they help to prevent strangers or dangerous people even to come into the party, or when they have secretly slipped in, they will help to remove them fast. With this team of researchers, we study the effect of microplastic fibers on these lung cell types. And for this, we firstly produced microfibers made of nylon and polyester. You can see them here. They are very small. They are approximately 100 times smaller than a millimeter. And then we were curious to see what the security or the macrophages do with these particles. So what did we do for that? We stained the fibers with a red dye, and here we stained the nylon fibers, and we added them to the green macrophages. And then we made a movie to follow overnight what happens. So you can clearly see that the green macrophages are hunting the red fibers. They are very busy trying to eat them. So at this point, we can already conclude that the lung cells strongly respond to the presence of these fibers, because you can see they are very busy trying to eat them. In our lab, we developed a model for mini lungs in a dish. And for this, we grow epithelial cells and fibroblasts together, and this way we are able to obtain two distinct types of mini lungs. So firstly, we have a nice round structure that represents the airways. And second, we have a smaller structure that has a grape-like form, and those represent the alveoli. And those mini lungs are a very nice model for us to study the effects of the microfibers on human lungs. So here you see both mini lung structures present in our dish. So the blue arrows indicate some airway mini lungs, and the pink arrows indicate some smaller alveolar mini lungs. And when we then add the nylon microfibers, we see an enormous effect. So what we are looking at are mainly microfibers, because there are hardly any mini lungs present, and the ones that are there are much smaller. So the blue arrow shows some small airway mini lungs and some small alveolar mini lungs, but the effect is enormous. Whereas when we add polyester microfibers, nothing or hardly an effect can be seen. So you have nice round airway mini lungs and also normal alveolar mini lungs present. And that is also what I show you here in this graph. So we counted the number of mini lungs present, and this is specifically airway mini lungs. And then you can clearly see that there's a huge effect caused by the nylon microfibers. So when we add these nylon microfibers, there's an enormous reduction in number of airway mini lungs present as compared to the situation without fibers. And we hardly see an effect for polyester. And this is mainly on the airway mini lungs and not so much on the alveolar mini lungs. So coming back to everyone's daily morning struggles in front of our closets, by wearing synthetic clothes, we contribute to the plastic pollution because microfibers are released to the environment. And we know that those fibers are inhalable and are actually found in human lung tissue. And today I show you that the lung cells strongly respond to the presence of these fibers. And moreover, that the nylon microfibers have a negative effect on the mini lungs. But what does all of this mean? That it's bad for nylon clothes? Well, I would say not yet, because these results are a simplification of what happens in reality. We don't know how much we actually inhale, but probably the concentrations that we are exposed to in daily life are much lower as compared to the concentrations that we use in our laboratory settings. However, it does mean that these microfibers are maybe not as harmless as we used to think. And it is therefore that I want to raise awareness and do further research to be able to estimate the risks to the human lung health. I would like to conclude with some free advice from my side, In the meantime, make sure that you ventilate your house well and open the windows regularly so that you can ventilate. Thank you for your attention.
Thank you very much, Francine. I saw you last Sunday on Nieuwsuur, the current affairs show in the Netherlands, for those who don't live here. And to me, as an outsider, it sounded all very alarming. You told this story in a nutshell. Were you alarmed when you saw your research results in this scientific research that you did?
Yeah, well, we didn't expect this to happen, to see an enormous effect. As a researcher, you're always happy if you see something happening, but this we didn't expect. But we weren't alarmed in the sense that we were afraid for the whole human health because, well, like I said, the exposure that we use in our lab is way higher than what we have in our lungs.
So what should we think of this? I mean, you're not alarmed? I mean, because the messages are sometimes confusing this morning.
Yeah, I see.
And I try to make sense of it. When you see it, it is alarming. But are you saying, don't be afraid, nothing will happen?
At this point, there's no need to be afraid, but we do need a lot more research because we do see effects and we need to find out what does this mean to us, to our health. So yeah, for this we really need more research.
And do you? Will you continue this research? Is there money already in the pocket at the university to continue?
No, there's hardly any money for the research at the moment, so it's urgently needed.
What would you like to, where would you like to go from here?
Yeah, I think the fibers that we use now are reference fibers, so we made them in the laboratory setting. They are very standardized, so I think it's important to test the fibers that we are exposed to in real life, like fibers that are coming off our clothes, for example. And I think it's also very important to have a look in human tissue to see what is there and what are we actually exposed to.
Naturally, in your field, you hope to find nothing.
Yeah,
is
that's
that true?
Kind of a een gewetensvraag.
Yeah, I mean, I can see how you are excited about the results, but the results could be very negative for us.
Yeah,
right?
True, yeah.
Okay, I wish you a lot of luck. And also, how old are you?
Almost 30.
Almost 30, you're very young, and what is interesting to me today is the subject, but also that a lot of women are involved in the research.
Yeah.
Almost everybody on this stage today.
Yeah.
Is that just by coincidence?
No, it's because women are better in general.
Well, thank you very much. Missy is from Canada and she's working at the University of Utrecht. Juliet Legging.
Wow, good morning. What a pleasure to be here. It's quite exciting for a scientist to be here at an occasion like this, in a forum like this, a venue like this, trying to tell you a bit about our very, very young project on determining whether or not microplastics actually get into the fetal environment, and if they're in the fetal environment, do they actually cause effects there? So I'll take these few minutes just to introduce our project, a little bit of the background, why we suspect that microplastics could get into the fetal environment, how we approach our project, and some preliminary results. You'll see some important people in the project as we go along, but I wanted to start actually with showing this important person first. And this is my daughter. In this ultrasound, she was 6 months old. In my tummy, of course, and I remember this day very, very clearly still. It was 14 years ago. My husband and I were so excited to see a baby already this big. It was the first ultrasound that we'd had of a 6-month-old baby. We could see her, we could picture our child, and we could hope and pray that she was healthy and that she would develop into a very healthy young woman, which she has, luckily. I am a toxicologist, so I have perhaps the disadvantage of knowing that in the uterus during development, the fetus is extremely sensitive to exposure to chemicals. I've worked now for about 20 years with the class of chemicals called the endocrine disrupting chemicals. And these are chemicals, different classes, that can disrupt hormone systems, that when, especially during development, during fetal development, when the timing of hormones is really important for the proper development of tissues and organs. So I've already known for a long time that chemicals in plastics, for example, bisphenols and phthalates, when the exposure is during these sensitive periods of development, they can lead and they can play a role in disease later in life. So when thinking about microplastics, and I'm very new to the field of microplastics, I of course am asking the same questions that I asked already in the last 20 years. Are these microplastics making it to the fetus? Are the chemicals that are in the microplastics leaching? And what is the potential health risks? And really, we don't know yet, and I'm really excited that we have some funding to work on this important topic. So, this is the picture that we're seeing. This is the symbolic picture that the Plastic Soup Foundation has used to represent our meeting today. And it's a very scary picture, right? It's a doomsday scenario where our children during development are not only swimming in fluid containing microplastics and the chemicals associated with them, but they're also actually made up of these chemicals. And of course, these pictures are an extension of what we've seen in wildlife, in marine wildlife, turtles, birds, that we know that there are plastics being taken up. But really, we do not know yet if microplastics actually reach the human fetal environment and the human placenta. What do we know? And why is it that I, together with a fantastic group of researchers, actually hypothesize that these microplastics will make it through the bloodstream and enter the placenta where the baby could be exposed? The reasons, there are actually two lines of evidence. The first line of evidence comes from what we've already heard this morning, that we know that air pollution is made up of very tiny particles, and that those particles can enter our bodies. In this really hallmark study that came out just a couple of weeks ago, researchers have shown that air pollution, in particular these little black carbon soot particles, nanometer size, are actually found in the placenta. So there's the proof of principle when it comes to air pollution particles, that they do reach the placenta. We know also from animal studies that when we inject mice, pregnant mice, for example, with polystyrene beads, we inject them, in this study, only 4 hours after the injection of the pregnant mice. These fluorescent particles, fluorescent plastic particles, made it to the placenta, and not only were present in the placenta, but what you can see here are these little fluorescent beads showing up in the fetal brain, in the fetal liver. So animal studies are giving us indications that indeed our hunch may be right, that these microplastics might make it. But I would like to re-emphasize that we really don't know yet for humans, and we really need to answer these particular questions. So we need to know, do the microplastics reach the placenta and the amniotic fluid? So here you see the human fetal environment, very much simplified, with the baby in the uterus, the placenta, which forms the really interesting organ. That's really a temporary organ, only formed during pregnancy, that gives the baby all of its nutrition, important for metabolism of steroids and other molecules, important for the elimination of waste out of the baby into the mother and out of the mother. And the amniotic fluid being that the water surrounding the baby, really important for cushioning the baby, also for metabolism, elimination of waste products. We know that if a microplastic would enter the amniotic fluid through the placenta, the baby would be directly exposed. The baby swallows that amniotic fluid constantly and pees it really out again. So we need to know, is it in the placenta? Is it in the amniotic fluid? Because then we know there is real fetal exposure. And we also need to understand if those placentas, if those particles make it into the placenta, will they cause harm? And will the chemicals that are associated with them cause harm? So those are the main research questions in our project. We started about 4 months ago, so it's very early for us. What we did was we got together a very multidisciplinary team of scientists. And as Dick Spethak said this morning, the only way to approach these complex questions is to get people with different expertise together, working together. So what we have here is an extraordinary team. We have a pediatrician from the Dijklander Hospital in Hoorn, Gavin Tentusser. He's collecting, as we speak, collecting placentas and amniotic fluid samples from women who are delivering babies under his care. He's providing those placenta and amniotic fluid samples to our chemists. We have different groups of chemists involved. Maria Lamoré and Heather Leslie from the VU University in Amsterdam, and Douglas Walker from the Icahn Medical School in Mount Sinai in the US. Two chemistry groups using their own specific sensitive methodologies to measure these microplastics in placenta. We have Dick Spethak providing us the most environmentally relevant plastic particles. As you heard this morning, we need to be looking at the particles that we are exposed to as humans. And so Dick's group is taking different kinds of plastic particles and weathering them and providing them to us, the toxicologists in Utrecht, to look in placenta cell cultures if these really environmentally relevant particles enter the placenta cells and may cause effects there. So just quickly, the chemistry that's involved, we're using these two different labs, one in the Netherlands, one in the US, each with their own specific expertise to measure plastic polymers in the placenta samples and the additives that are in the placenta samples, in addition to Raman spectroscopy and advanced microscopy. So we can compare methods, we can find out which method is the most sensitive to quantify these plastics, and we're still busy developing methods and collecting our samples, so I'm afraid I have no results yet. In our lab in Utrecht, thanks to some additional funding from Sonnenweg, we've been able to team up with our imaging facility in our university. They have really the best microscopes, the really high power microscopes that we need to image these placenta cells. These are human placenta cells that we can culture on a petri dish, and we can expose them to different plastic particles, and we can look at if human placenta cells take up those particles and if they cause any damage or harm to the placenta. So this is a 3D image that just was created yesterday. I got to explain it to you, maybe I'll show it to you in a moment again. So those little pink balls are actually polystyrene 200 nanometer beads that we have added to these placenta cells in a petri dish. And we can, this way we've actually been able to show that these particles are inside the placenta cells. These are placenta cells. The yellow coloring shows the protein in the cells. The blue colors is the nucleus of the cells. So if I can maybe show it one more time, I don't know if it's going to work. I love this. This is really hot off the press. Students have been working all week to show that those little, watch them now, the little pink polystyrene beads are really inside the cells. They're not on the membranes, they're not on top of the cells, they're really taken up by the cells. So for us, this is really the most important first step in understanding, okay, so the particle gets into the cell, what happens to the cell afterwards? How does it react? And what can be the possible toxic effects of the particle and the chemicals associated with the particle. So really, to understand the risk of microplastics to the human placenta and the human fetal environment, we need to follow all of these steps. We have a year in order to understand something about the exposure and something about the hazard. It's a first step, and it's really crucial in order to understand more about this potential risk. And if indeed this is a scenario that we could really see as a realistic scenario if we continue to go on the way we are now. So let's take care of the next generation by continuing this research, by continuing what you're all doing. And I really want to thank the team working with me on this, and to thank Sonnenweg in particular for funding this really high risk but really exciting research. Thank you very much.
morning, everyone. We've heard that we've been measuring chemicals for a long time that come from plastic in the human body. In fact, my first gig after I got my PhD was measuring brominated flame retardants in the blood of European parliamentarians. That was helping them, they were all a little bit plastic, and they got to think about this as they were debating the chemicals legislation, REACH, which is now in place since 2006. But today I wanted to talk to you not about the chemicals, but the possibility of plastic particles in our blood. And this is the wrong slide. I don't know, would you like me just to do it without slides?
Yeah.
Or, I mean, this is the wrong presentation. This is for this afternoon. Would you like to see slides, or would you like to just...
Slides. Slides.
Okay, I'm just going to continue. I'm not seeing anything from production, whether we should stop and do another presentation. Or... okay, I'm just going to continue. Who here knows about the Lennox globe? That's not the right one either. Sorry, I have 3 presentations today. The title is in the... anyone here know about the Lennox globe? It's a very old picture of the Earth, and when old cartographers were drawing the map of the world, they came into areas where it was called terra incognita, and they didn't really know what to fill in there, so they put "here be dragons," and they had dragons there. And I must say we are venturing into a sort of analytical terra incognita here when we're trying to measure microplastics in human matrices. And I would say that this kind of microplastics exploration is like a research voyage for very brave analytical souls. After many years of trying to frame the plastic pollution problem as not just something from the oceans, but also something for us, I was very happy 2 years ago to hear at a stakeholder conference in Brussels that Frans Timmermans said, we haven't even charted the effects of microplastics in the proper way when it comes to human health. And I'm going to talk about charting not only effects, but also exposure. Because for effects to happen, you need to be exposed. Dick showed the slide earlier, and I had a slide somewhere, that shows that exposure times hazard or toxicity equals risk. So what we do normally is we start looking at exposure outside our body. And we knew when we started about 10 years ago or more, now time flies, to study microplastics that we couldn't use, for example, tap water when we were working with our samples, because we knew that tap water would contaminate our samples and increase our blank levels, as we say. Then about 5 or 6 years ago, we were approached by the only people who are interested in sponsoring our research into food and drinks from the supermarket, and they were TV shows from Denmark and the Netherlands. And we started looking at what's in beer and Chardonnay and honey and various products. Also, we looked at oysters and mussels, and we were finding microplastics basically in all of these food products that we were looking at. We also knew about air contamination studies, and there was some early work done on this. There aren't that many dedicated to finding microplastics in the air, but we do know that the dust that we normally measure contaminants in our lab, that contains a lot of plastic. So I had, hey, there's me. I had a slide about external exposure, what we know so far. And there's been a few recent attempts to quantify what's in our food basket. So if you eat a lot of stuff and you drink water, what can you find in your body? And if you look at this data, there's a lot of variation in the data, and there's a lot of uncertainty in the data, and even the people who produce these reports will tell you that there's a lot of uncertainty at this point. And One of the reasons for this uncertainty and what we're working on is what we call QA/QC, the quality assurance and quality control. And I'm happy to say that we have started last year an initiative to do what we call interlaboratory studies, and we want to do development exercises to help labs show their proficiency in measuring microplastics, and there's also some efforts to make reference materials, and these are really what we call QA/QC tools, which the analytical community really needs. And this will boost the comparability of the data and allow us to make better comparisons. There was one also famous study that came out last year, is how much microplastics is in human feces, and there are about 2 particles per gram off the top of my head. And these are the particles that we're not worried about, because these are the particles that are not going to be absorbed by your body, and they're not going to get stuck in a tissue, and they won't lead to chronic inflammation. They are a headache for sewage treatment plants instead. What I'm interested in is measuring real-world microplastics, as I said. This gives meaning to the toxicity data. Sometimes I call them wild microplastics, so the plastics that come off your clothes and you breathe in, and plastics that you consume with your food. This is our analytical terra incognita, and I'm happy to say that we are making quite a lot of progress at our lab, and we're not quite ready to show you the results yet, but we are in advanced stages, and we hope to publish very soon what we find from our initial screening studies. I wanted to note that there have been reports of, old reports even, of knee and hip replacements, which are polymeric materials, and they crumble at some point and start leaving the prosthetics and going into your body. And we already know that once they're in your bloodstream, they can be transported to different organs. They're mobile in our bodies. And we know from really old, obscure studies where they were feeding plastic particles to animals that within a couple of hours, if you looked in the bloodstream, you would see these plastic particles in these animal bloodstreams. And then after that, you could also find them in organs. So this is really leading us to have a hypothesis that if considering we are exposed, we will probably be able to detect microplastics in our blood. What would such a finding mean? Well, what we would be interested in is knowing what range of plastic particle concentrations are we finding from these wild microplastics in our blood, and how does that compare to the range of effect concentrations that are coming out of the toxicity experiments? And we hope that the real exposure levels are much lower than effect concentrations. But the thing is, we've got to measure it. It cannot be predicted. I would like to just, because of this inability to predict what the effects will be, I'd like to touch upon some of the recent reports that have reviewed all the literature, and it's a limited body of knowledge, and everybody acknowledges that it's limited so far. But still, for example, SAPEA stated in their verdict, which is the word they use on their website, that there's no widespread risk to humans and the environment. And as Dick said, the WHO wrote that humans have ingested microplastics and other particles in the environment for decades, with no related indication of adverse health effects, or there is no evidence to indicate a human health concern. So if the soundbite that we all pick up from this is that there's no risk to humans, I think we are making a certain error of logic, which is quite common, and it's been known, it's been first termed in 1600. I looked it up. It's called the appeal to ignorance fallacy. And that means there is no evidence against X, therefore X. And here, it's important to remember that an absence of evidence is not the same thing as evidence of absence. And I think that's a problem, and Bertrand Russell, the philosopher, agrees with me. He wrote a long time ago that such logical errors are of greater practical importance than many people believe. they enable their perpetrators to hold the comfortable opinion on every subject in turn. And I think this is not the time for holding comfortable opinions that there's, for example, no risk. So I think it's important to get our communication right. In the meanwhile, we're dealing with our analytical dragons, and we're very confident that we will be able to present some results soon. But everybody's asking what to do in the meantime. Everyone wants to know. And what I do, I've had this sort of thing happen before, I look to the European Environment Agency's research, and such cases as we have before us today calls for the precautionary principle. Many of the early warnings that have been studied by the EEA have turned out to be legitimate problems. In fact, they say that the EEA says that false alarms are very hard to find in our history. And I think the last thing that the world wants now is another environmental nasty surprise. We don't want another large-scale, long-term threat to human or ecological health. But right now, we are flying blindly. And this should be enough to raise a policymaking eyebrow, and we hope maybe even a research funding body eyebrow. And we scientists that you're going to see here on the stage today, we really want to reduce the blind spots in our knowledge, and we need your support. I'm working at the VU in Amsterdam, Heather Leslie. There's the only one Heather at the whole VU, so I'm very easy to find. Please check out our website for all of our plastic projects. If you know of anybody or if you are interested in joining in our interlaboratory exercises, please get in touch. We'd like to hear from you. We have to do this together. And I'd like to thank all of the organizers of this summit, especially the Plastic Soup Foundation, and of course a big thanks to our research sponsors. Thanks.
Long, long ago, there was this gas. It was called miasma. And everybody believed that when people died, that the cause was miasma. And not until research was done and funded, it occurred to people that it may be something else. There were little particles, not microplastics, but pathogens, bacteria, viruses, through air, through water, that caused these large epidemics. Cholera, Spanish flu, and what I hope is today that we find that the research is needed to find out whether microplastics can be a concern, a major concern for public health. I must admit, last week I was at the World Health Organization in Geneva, where that blasted report came from, with this very complicated message. And there we discussed how to use water safely in irrigation. And we probably need to understand that worldwide, wastewater is largely untreated. 20% of all our wastewater is actually treated, which means you can do the math. We're not very good at percentages, but you can do the math. How much is left that goes into our environment untreated? 80%. A 10 for math. So what are we worried about? We are worried about very small particles, indeed microplastics, but maybe nanoplastics in our environments that are put there by us every day, the whole day, all the time, and have been done for centuries, as we heard this morning. What we're worried about is those plastics themselves. What we're worried about is everything that's in it, the toxic substances that we just heard. And me, or should I say I, I am worried about what's on the microplastics, because actually what we've learned is that on the microplastics, microbial populations may grow. There may be bacteria, there will be bacteria in the environment, that can actually use these microplastics as a service, and a very good service at that, to grow on. This is what we would like to find out. So are these biofilms or microplastic particles actually a cause of any human health concern? Well, I have to admit, they probably do. Why? In our rivers, also in our Dutch rivers, but as we've seen pictures, mostly also in other countries, we have widespread pollution. And this widespread pollution comes from our wastewater. That's what we just learned. But it also means that it carries our waste, so whenever you go to the toilet, remember me. All these pathogens that we carry, whether we're sick or not, will be flushed down the toilet into our rivers. So in these rivers, plastics or no plastics, we'll have pathogenic bacteria, viruses, and parasites. And they will be moving, they'll be flowing with the river flow into the sea, which if it goes far enough, is not really a problem. But however, what about these pathogens on the microplastics? They may behave differently. So that's our hypothesis for our research. Should we be worried because these pathogens, although they're in the river, they can also be on these plastics. And on these plastics, their mobility may be increased. I forgot my slides. I got into the story. So, are we worried about pathogens? And I haven't really explained this, but there may also be virulence and resistance genes. And as we all know, antimicrobial resistance, alongside climate change, is one of our major worries. What if these resistance genes travel further along the route on these microplastics than they would normally do when they attach to other particles and maybe go into the sediments of our rivers? Well then, so this we really want to find out. We know that besides exposure to water, exposure to air is also a grave public health concern. Actually, in the Netherlands, we now have wastewater treatment plants that emit Legionella bacteria in aerosols, and they may reach people that live not even that close to these wastewater treatment plants. Is this a problem? Well, we are actually on it, so research is being done. But how do these microplastics play a role in this? We know there's all these different transmission routes for infectious diseases. Now we want to find out about the microplastics. So what are we doing? We're sampling the River Rhine in this case, just a few samples, it's a pilot project. But near the border with Germany to see what comes in. And also near sites where we have recreational water activities, intake of drinking water treatment plants. And so we were wondering, can we isolate DNA and then look into whether we can find these virulence genes? Can we find antibiotic resistance genes? Well, I must admit, I'm a bit worried, but yesterday, yes, we did find resistance genes on the plastics. Nothing unusual, we find them in the rivers, they'll be on the plastics, but do they travel further or differently than they did before? So we worked together with KWR. They do our microplastics analysis, they perform the sampling, so I'm very grateful to work together with Patrick Bauerlein, who's been very active over the summer, and with Rosemarijn van der Plaats, who is a real expert in next generation sequencing. And they found actually some results. They found the resistance genes, and we did find that in the larger microplastic particles, actually they sort of seem to be differently in their profile as compared to smaller particles. as compared to the surface water itself, the river water. So that's what we need to find out. I have some things that I don't want to leave unsaid. So one of them is actually, they were not completely sure whether this different mobility is actually a problem, so we need to find out. The other thing was also already mentioned, does exposure to pathogens and genes on plastics, does that lead actually to different or additional health impact? I'm not sure. We need to find out. But we need to collaborate, and so that we'll do. We're going to find out if these genes and these bacteria, these pathogens on these plastics, if they have a different result on the immune system, if combined with microplastics, together with researchers that are actually also in our National Institute of Public Health and the Environment and at Utrecht University, where I'm a professor. And lastly, I should also mention this. What about global impact? As I mentioned at the start, we are worried about all this waste and all this wastewater goes into our environment and all the plastics and pathogens that go with it. So shouldn't we also be worried what happens in other countries? Well, we do. So we work together with the World Health Organization. I'm actually the director of one of the WHO collaborating centers. And what we do is we look into risk assessment of pathogens in food and water, and we try and find solutions also for people that do not have wastewater treatment, that do not have a good public health infrastructure. And being a woman, I almost become flooded with tears because we really have to do something. Thank you.
Good morning. Today, I would like to tell you something about a project that I'm doing, getting funded by SonMW. I'm doing this work together with Professor Kundeman and also with Giulio Giusterini, who is a postdoc working on a project performing actually all of the experiments. So hopefully you can actually see this picture soon. And what I want to tell you about, what we're interested in, so indeed here is Giulio. What we are together interested in is how immune cells deal with microplastics. And why do we think that this is an important question? So in order for you to understand that, I need to give you a little bit of background on our immune cells and on what they normally do in our bodies. So what if you have a wound? If you have a wound, sometimes bacteria can penetrate this wound, and these bacteria need to be taken care of, attacked by your immune system in order to not get an infection. So here we can see the bacteria entering the wound, and what now happens? What now does our immune system do to attack these bacteria? So what I have here is an intravital microscopy picture. That sounds a little bit complicated, but what it is a living mouse under anesthesia under our microscope. And that way we can visualize in this living mouse how immune cells are dealing with bacteria in this case. So in blue here you can see the tissue of the ear of the mouse because I injected the bacteria in the ear. And in red you can see the bacteria, and in green the immune cells. So what you can see when I start playing this movie is the immune cells starting to attack the bacteria. I'll play this movie, it's about half an hour in real life, but I'll play it a little bit faster for you now. So this is what happens. Your immune cells in green are really swarming to these bacteria in order to contain them. If we now zoom in on this process a little bit more, you can see that these immune cells actually are like Pac-Mans and that they can engulf the bacteria and take them along. So if you can look at the top particle, I will play it one more time. At the top you can see the red bacteria being engulfed by the immune cell, and then all of them are being recruited to bigger colonies of bacteria, after which these immune cells can degrade these bacteria. But what now happens if in our bodies we have microplastics? So researchers before have already shown that if you orally administer microplastics to mice, that these can end up in different organs. So here you can see that they end up in the liver, the kidney, and the gut. And to me, it was a surprise that even the 20 micrometer microplastics ended up here. And to you, I think 20 micrometer doesn't say a lot, but to me, it's actually bigger than a normal cell in your body. So that means that even microparticles that are bigger than your cells are able to penetrate your body and enter the organs. So this really prompted us to ask the question, what now if immune cells are encountering microplastics rather than bacteria? Will they also start to involve them? Will they degrade them, which of course they actually cannot? So how do they deal with it? Do they try to attack them but they cannot? So this is what we wanted to investigate. And in order to do this, what we did is we isolated blood cells from humans, from human volunteers. We put them in a culture dish, and then we put them together with actually 4 types of microplastics. So we chose to look at 2 sizes, the 1 micrometer and the 10 micrometers. The 1 micrometer is about the size of a bacteria, and the 10 micrometer is slightly smaller than a cell. But then in addition to looking at clean microplastics, we wanted to look at another situation, because normally actually microplastics are not clean. They tend to stick to many things. So we were thinking that if we would encounter microplastics in our body, it's much more likely that blood components will start sticking to these microplastics and perhaps changing how your immune cells are dealing with them. So we also thought it was important to not only look at the clean microplastics, but to also look at the microplastics that had these sticky blood components added to them. So this is what we did. And here you can see a microscopy picture. Now in gray are the immune cells, and in green are the microplastic. These are the bigger beads. They're about the same size as the cells are. And what we can see in the uncoated or the clean microplastics, that the immune cells bump into these microplastics, but they're not engulfing them like they do with bacteria. But then, if we have the microplastics that are coated with the blood components, we see a very different picture. We can see here at the bottom that, and also in some other cases, that now these microplastics are being engulfed by immune cells. But what was even more troubling is that we could see the cells dying, and that you can see in this movie with a red signal. So you can see gradually in this movie, also the cell there at the bottom that had engulfed the microplastic is now starting to die and flashing this red signal of death. So that was worrying to us. Then if we compare that to the smaller microplastics of 1 micrometer, about the size of a bacteria, we found that also they were being engulfed by the immune cells, but in this case we couldn't detect the death signal. So it seemed like really the bigger microplastics were giving a bigger impact. We also did the same experiment, well actually with another experimental setup, but at least to also see if we could find this increased cell death in a different method. And indeed what you can see here is in the black line, immune cells only. So this is how long a normal immune cell lives. We have on the x-axis, on the horizontal axis, we have the time, and on the vertical axis we have the amount of cell death. So if we focus on, for instance, the 20-hour time point, you can see that immune cells only have hardly died, but in case of the 10 micrometer blood plasma coated line, you can see that many of the immune cells had already died. So what did I tell you today? I showed that if a microplastic is clean, not covered, that it's being ignored by immune cells, and that if it's covered in blood proteins, that now they can be recognized by immune cells, and that in the case of the bigger microplastic, this causes it to die. And we've only been working on this project for 4 months, so there's really a lot of work to be done. And the things that we first want to do is to look at particles that actually are there in the environment. So DIG provides us with samples, DIG Fetal, that actually have been exposed to UV light and to seawater, to better mimic the environmental plastics, because that sort of erodes their surface and can really change how an immune cell is dealing with them. And also, already mentioned before, we want to see different shapes, not only spheres. In addition, I think it's a very important next step to look in these mice, again under anesthesia, under the microscope, to see if in a real living animal also this microplastic is coming together with an immune cell. Because now we've looked at it in a culture dish, and we are not really sure if this would happen in a real life situation. Therefore, I think it's key to orally administer microplastics to mice, see if they arrive in the blood, and see if they arrive in organs, and also visualize how the immune cells are now dealing with these microplastics in the body. In addition, we got some extra funding to work together with Frekarisse and Leron at the VU, where we are now adopting one of their methods where they've measured silicon in tissue to see if we can measure microplastics in human tissue biopsies. So I'm also very excited to pursue that. So thank you for your attention.
Nienke, thank you very much. You were on this news show as well, Musical last Sunday. Again, the question to you, when you found out what you saw, and what you just told to us, were you shocked?
I was shocked in the sense that I hadn't expected that the different microplastics would have such a different result, and I actually initially thought that the smaller the plastic, the more dangerous, and we actually found the opposite. And I actually thought I probably would find nothing, and we found increased cell death. So I really think it warrants more research, because now we're not sure if it will actually happen in our bodies.
I like how all of you are very cautious. You're not like, I would normally say, the boy who cried wolf, but you're not the girls who cried wolf. But it is alarming to see what you found after such a short period of research. As you said, 4 months, it's nothing.
Yeah, it's true. 4 months for research is really short. And I still think that because we did the culture dish experiments, it's feasible in these 4 months to draw conclusions from that. But to take it further to human health, for us at this moment, it's too early.
I understand, but still the $1 million question is, if you do more research and you find these results in the human body, what is the implication of that?
So if we would find it in the human body, I think it also depends on the exposure. How often do we see this? Because if you see cell death in the body, you can see often that it recruits even more immune cells, because it's sort of a danger signal, like something is wrong. So then you can imagine that you will get an accumulation of all these immune cells and this infection.
But is it correct to say that then our immune system is seriously affected by this?
I would say affected, and not seriously yet until I've seen the evidence. Yes.
I hope it won't be serious.
For sure, yes, I really hope it's not.
As you hope you didn't get the result that you just got now.
Yes, exactly, yes.
Thank you very much again, all of you, by the way. And for now, there is a short coffee break. There are more people on stage. After that, you will hear a gong. And please come back to the hall, because then it's the signal that we start again. Thank you for your patience. Hope to see you.